All right, as obvious as our previous model looks like, it is not a realistic model. So we are going to add some elements to that. N sub t is equal to birth rate times n sub t minus 1. In fact, for the purpose of showing this, I believe it's better to say n sub t plus 1 b times n sub t. I want to keep the right hand side cleaner. Okay, so this is the original model, and this is not realistic, and we want to make it more realistic, obviously. Instead of multiplying by the birth rate, so I'm going to change the model to nt plus 1 is equal to b minus d times n sub t. So now this time this is a more realistic model because b is the birth rate, d is the death rate, but this is not enough. This is just the death rate. What about the sources that this population has? Food is scarce, so as the population grows, it's getting more difficult to basically acquire those sources. Therefore, let's make one more change here as well. So this time n sub t1, it's not just the birth rate and death rate, which we just added, but also n sub t and this one basically minus, let's put this one small letter d of t. So what is this dt? dt or d sub t is defined as n sub t squared divided by n max. N max is maximum population. Scientific term, this is the same thing as carrying capacity. The reason that we have nt square is that for every given number of people we have, we are going to have n to the power of 2 interactions. This is the number of these links that existed. So the number of interactions is added. What is this n sub t squared divided by the maximum capacity or carrying capacity? That's the number of disses because of the lack of resources. So these two formulas that I'm going to write down now are exactly the same thing. So let's call this b minus d r as a rate. Obviously, if the death rate is 0, this r is going to turn just to the birth rate. And then r times n sub t minus n sub t squared divided by n max, which is the carrying capacity. And this is the formula. Now, since we have an exponential here, and this is added to our original model, this model is not going to be linear anymore. And this model is going to show a different behavior compared to the previous model. Let's look at it. And this happens because, just one more thing to quickly explain here. In the linear one, we have superposition rules, which is a function of x plus y is equal to fx plus f of y. So this is the superposition rule, which means a function of two variables, f of x plus y, is equal to f of x plus f of y. And then we have an attribute of homogeneity, which is f of c times x is equal c times f of x, and c being a constant. You can put a number 2, for example, 3, 4, whatever number you want. And this is a function of c times x variable. Based on homogeneity principle, this is equal to c times function of that x variable. And when basically superposition or homogeneity or both of them fail, we do not have a linear model anymore. In our previous example, n sub t plus 1 being equal to b times n sub t, both of these principles of superposition and homogeneity hold. Whereas in the case of nt plus 1 equal to r times n sub t minus n sub t squared over n max, we cannot, these basically principles would not hold, and we have a nonlinear function. And the reason that we have a nonlinear function is rooted in feedback loops. But let's quickly check the simulation model we have. Okay, so we are going to test this new model with this simulation we have. Let's start with the initial population of 1, similar to the previous one, birth rate of 2, and death rate of 0. So basically reducing this to the similar to the previous one, because r is equal to b minus d. In this case, d is 0, therefore our rate is going to be the same as birth rate, which was in the previous model, and we set that to 2. The only different thing here is the carrying capacity, that we are basically fixing it to 60, so that's the maximum number of population. And we are going to do this with the rabbit population basically in this simulation. This model also known as logistic model, and you are going to see why we call this logistic model. So after initial setup, if we have one rabbit, if we go one step, so at initial time we have 1, at time 1 we have 2, time 2 we have 4. So far it's so similar to the previous one. But at time 3 we have 7, which doesn't look like similar. 4 we have 12, 5 we have 19, goes like that. 7, at time tick 8 we have 30 rabbits in our world. And let's just push this one more time, and at time 9 we see we still have 30 rabbit. Now let's check these and see how they are different. The first one is the relationship of last year population to this year population. As you can see, it is not anymore a line. Rather it's similar like to a logarithmic function. This is sublinear kind of function that shows that in the initial stages it grows like for 1 unit change in the last year population, we see almost 1 unit change in this year population. But towards the end, as you can see, for 1 unit increase in the last year population, or this year population increase less than 1 unit. So that's how this model works. So this is a nonlinear model, unlike the previous one. And as a result of that, we also have a different as a result of that function, we also have a different relation between time and population. This is not anymore exponential. Rather, it starts like exponential but ends as S-shape. Also, this is a sigmoid function, also known as logistic function. That's why this is known as logistic population function, which starts slow and then suddenly grows so fast, and then it reaches to the maximum, which plateau at the end. You might have seen this figure before. This is like for infection, like pandemic that we had. After the virus reaching to the entire population, or whatever left of the population, if anyone else is immune to the virus, it's plateau at the end. One last thing that I want to show you in case of this model is that this counts 30. So you saw that at time 8 we had 30 rabbits, at time 9 we have 30, at time 10 we have 30, time 11 30, and if I continue this, like let's say up until time 20, nothing changes. This remains 30 rabbits. So you might ask, we had the carrying capacity on 60, why are we having only 30 rabbits? N sub t plus 1, we have r times n sub t minus n sub t square divided by n max. And this was the formula that we were using. Now, in this case, at any time after time 8, we are using the birth rate of 2, so that r is 2, and since there is no death rate, r and b are the same thing, so 2 times the previous population was 30, already we saw that, minus 30 square divided by 60, which was the carrying capacity. And this is equal to 2 times 30. So 30 square is 900. And if you divide that by 60 is 15. And this is equal to 2 times basically 15, and it is equal to 30. So it doesn't matter how many times you pass that in this one time 8, we are going to have 30 rabbits, not the 60, which was the carrying capacity. So it's always going to be less than that. For example, if I change this 50 to 80, you see at time 7 we have 39, already passed. At time 8 we have 40, and then time 9, 40 again. It's stuck with that. So the value can be different. Now the thing I want to check here to see if we have a linear function or not, which we know we don't, but just in case. So if we have initial population of 1 with a birth rate of 2, death rate of 0, and 60 carrying capacity, if we set up this model and reproduce, in the time 1 we have 2 rabbits, time 2 we have 4, and time 3 we have 7 rabbits. We already talked about this function that is not linear. Let me again zoom in for the better view. So we already know that this is not linear, and it is actually sublinear because it's a logarithmic function. So if I increase this initial population by a magnitude of 4, so instead of starting with 1 rabbit, if we start with 4, and if this was a linear model, at time 3 we should have 4 times 7 or 28 rabbits. But since this is not a linear and this is a sublinear logarithmic type of function, I'm going to expect to have less than 28 at time 3. So let's set up. Now we start at initial time 0 with 4 rabbits, reproduce at time 1 7, we already passed the previous one, at time 2 12, and at time 3 19. As you can see, our value at time 3 instead of 28 is 19 because of the type of function we had, which is a nonlinear function. So again, this one shows that a simple function can result in a nonlinear dynamics due to the failure of superposition and homogeneity principles. So n sub t equal to b times n sub t minus 1, which was our original, produced a simple linear model. But this time n sub t equal to r times n sub t minus n sub t squared divided by n max resulted in a non-linear function. So in both cases, we had a simple deterministic formula, iterative formula, both of them. One becoming a simple linear model, one becoming a nonlinear model. Complexity sometimes can arise from simplicity. A simple iterative function similar to the function we had before resulted in a nonlinear behavior